Hello everyone, my name is Greg Poole from the Swinburne node of ADACS, the Astronomy Data and Computing Services Group, and this is a tutorial on high-performance computing with the gSTAR cluster at Swinburne University. In this second part of the tutorial, we will provide a basic introduction to the practices of working specifically with the gSTAR computing cluster at Swinburne University. This part of the tutorial will consist of an introduction to the hardware configuration of gSTAR, namely the node layout and storage setup, information about how to log into the system, an introduction to environment modules and how to use them to manage access to software on gSTAR, a discussion about quotas and how users can monitor their use of resources on the system, a detailed discussion of how to use the Q system on gSTAR, and finally, a quick look at the GANGLIA monitoring system with which the activity of gSTAR, both general and detailed, can be monitored. First, note that additional help regarding the use and best practices on gSTAR can be accessed by email through the HPC Help Desk at hpc-support@swin.edu.au or through the gSTAR homepage, supercomputing.swin.edu.au. The Swinburne Computing Cluster consists of two facilities: the GPU Supercomputer for Theoretical Astrophysics Research, known as gSTAR, and the Swinburne Supercomputer for Theoretical Academic Research, known as SWINSTAR, both of which consist of traditional x86 computing cores and GPUs. In practice, the two facilities are networked together as one system. Both interact directly with approximately 3 petabytes of Lustre file system. Accounts are open to all astronomers at publicly funded institutions in Australia and all Swinburne staff or students. All access to the gSTAR cluster is achieved through the head node G2, using the Secure Shell Protocol, or SSH. The head node's hostname is given here. Once a user is logged into this node, access to the rest of the system is possible. This includes a small set of 4 interactive nodes, with hostnames given here, which can be obtained through SSH. These nodes are shared by the entire gSTAR community and, as such, are intended only for small or quick tasks such as compiling code, editing files, or small test runs. The majority of the system's compute resources are managed through a Q system. We will discuss how to access this later in the tutorial. As is common practice, storage on the system is separated into 2 parts. The first is a small amount of user storage, which can be accessed from the user's home directory. Each user's allocation is 10 gigabytes. This is not a large amount and is intended for configuration files, source code, etc. Large storage allocations of 10 terabytes are available for approved projects. This storage is served from the projects directory. Please refer to the gSTAR homepage for directions on applying for project approval. As stated, gSTAR can only be accessed through its head node, as depicted here. This must be achieved using the Secure Shell Protocol, or SSH. Note that external access to the compute nodes is not possible. All access to the system must be conducted through the head node. Implementations of SSH are available on every computing platform. Listed here are 3 easily accessible options for Linux, Mac OS, and Windows. To demonstrate, let's log into gSTAR using the guest01 account. Using SSH, we specify the account we wish to use, followed by the @ symbol, and then the system we wish to log into, g2.hpc.swin.edu.au in this case. Once we provide the password, we are greeted by a system login message. It is worth monitoring this message since important changes to the system are sometimes announced here. Using the pwd command to see our present working directory, we see that we have been placed by default in the home directory of the guest01 user. Software on gSTAR is managed by environment modules, which allow users to dynamically modify their environment to access software that has been installed on the system. Advantages of environment modules include management of multiple software versions, handling of software dependencies, use of software installations that are optimized for gSTAR, and ease of use and reliability. Environment modules are accessed through commands executed in a user's shell. Each takes the form module, command, arguments. To get a list of all available modules, execute module avail. To get a list of all versions available for a specific package, specify the package name as well. To make a software package available with environment modules, they must be loaded. We show here, for example, the module load command to make a specific version of OpenMPI available. In this case, we are loading version 1.4.4 compiled with the GNU compiler. To load the default version of OpenMPI, we simply omit the version information. Modules will ensure that all necessary dependencies, like libraries, compilers, etc., are loaded as well. Listed here are the environment module commands needed to manage most user needs. Let's demonstrate. After logging into gSTAR, a module list shows that we have no modules loaded at startup. A module avail shows a list of all modules available on the system. Scrolling up, we can see that there are many. Let's load one particular version, version 1.4.4, compiled with the GNU compiler in this case. A module list shows that the module is now loaded. Suppose that we wish to load a different version of OpenMPI. First, we remove the loaded version using unload. Then we load the version we wish to replace it with, the default version in this case. A module list shows that the default version has been loaded. Also note, Modules is smart enough to realize that the Intel library is needed for this version of OpenMPI. It has gone ahead and loaded it as well. Users may have access to project resources on gSTAR. This includes their user storage and the project storage associated with any groups they may be a member of. This information can be queried using the groups, quota, and user quota commands. To demonstrate, we first get a list of the groups we are a member of with the groups command. The quota command gives a list of all the resources available on all the disk allocations we have access to, including our user storage on the home directory. The user quota lists only the storage allocated through the projects we belong to. The quota and user quota commands list a large number of values associated with our disk usage and quotas. These are summarized in this table. First, note that for each file system, usage and quotas in terms of total bytes and file counts are listed. There is a soft limit for each, above which the user has a specified grace period before which disk access to the file system is stopped. There is also a hard limit for each, above which access is immediately stopped. To launch a job on the compute nodes, users must create a submission script and submit it to the queue system. gSTAR uses the Portable Batch System, or PBS, as its queue management system. The command used to launch a job is qsub. Submission scripts for PBS are shell scripts with specialized PBS directives listed at the start. Shown here is the start of a sample PBS script available through the guest logins on gSTAR. PBS directives can modify the default behavior of the job. Here we see how to set the job name and the names of the files where standard out and standard error output will be sent. PBS directives can also specify the resources needed by the job. Here we specify the amount of memory, the number of nodes, and the number of processors per node required. PBS parameters and resources can be specified through a submission script or as options to the qsub command used to turn the script into a job. This table lists the most common resources users will need to set for their jobs. A complete list of PBS resources supported on gSTAR can be obtained by running man pbs_resources. Interaction with the queue system consists of submitting, deleting, and getting the status of jobs. This table lists the shell commands that perform each of these operations. Let's see how this works. Logged into a guest account on gSTAR, we move to the user's project directory. In this directory is a sample PBS submission script. Looking at it, we see that it specifies a number of PBS resources and then prints them to standard out. We add a sleep statement so that the job will take some time to run. Using QSub, we submit the script to the queue. Using QStat, we can see the status of the job. Since it is a small job, it begins running immediately, as indicated by the R for status. After approximately 30 seconds, we see that the job is no longer on the queue, indicating that it has finished. The specified output files are created, and we see that the output we asked for has been written to a .o file. In addition to the qstat command, the showQ command also presents a good summary of the jobs running or queued on the system. Interactive jobs can be launched on the compute nodes. This is particularly useful for intensive jobs that require interactive input. Examples include running demanding interactive MATLAB sessions or use of an interactive debugger with a large parallel job. To launch an interactive job, run qsub with the -I option, along with the options needed to specify the resources required for the session. In this case, our resource requirements are small, so the job starts right away. To demonstrate that we are now running on a compute node, hostname reveals that we are now running on the node gSTAR 057 and are no longer on the G2 head node. Echoing some environment variables listing some PBS resources, we can see the job ID we are running on, the PBS environment, which indicates that we are running an interactive job, and the wall clock time, which has been set to 900 seconds by default. We can then exit the interactive job and return to the G2 head node by typing exit. Lastly, remember to specify a project ID if the computing resources consumed by a job are meant to be billed to a specific project number. This is particularly important for resources acquired through a merit allocation scheme. To end, we take a quick look at the GANGLIA system, which provides a web interface for monitoring the activity of the cluster. It is available at this URL. It provides information about the cluster as a whole. Shown here as a function of time over the past hour are the load on the whole cluster, the memory usage broken down by allocation type, percentage CPU usage, and the send and receive network activity. A view showing a node-level summary of activity is also available. Here, each node's load is being shown. And a view showing a very detailed breakdown of an individual node is available. Finally, we reiterate that additional help regarding the use and best practices on gSTAR can be accessed by email through the Swinburne HPC Help Desk or through the gSTAR homepage.